Okay, so welcome back, and today we will be going over polar coordinates. Okay, and then we'll talk a little bit about also how to take the derivative of polar coordinates. Later we will talk about how to do integrations with polar coordinates, and then the whole section is over. The whole chapter is over, and so are the whole semester's courses, because this will be the last two sections we will be covering. Okay, so what is polar coordinates? Well, let's think about the other coordinates we know, which is called rectangular. Some people call it Cartesian. But basically what we have is, to represent a point in the plane, we set up a coordinate system as a benchmark, and then we kind of represent the relation, the location of the point to be the horizontal distance and the vertical distance. So this is your y, and this is your x. And if I tell you 2, 3, it's very easy to do. You just draw the rectangular coordinates and go 2 in the horizontal distance and go 3 in the vertical distance. You find it here. So that is where 2, 3. And then you know negative 1, 2, you know negative 2, 0. Okay? So that's what we have for rectangular coordinate system. Due to our experiences, the advantage of those kind of rectangular system is it decomposes things into horizontal and vertical. Therefore, it works really well with straight lines. Okay, for example, the straight line formula is really easy to write down. But then, think about all the motions we can have in physics. There is a different kind of motion, which is rotation, which is kind of hard to describe in terms of xy coordinates, because what you do is, for example, like the easiest one is circle. You have a formula like that. From here you can see number 1 is quadratic. So it's really difficult for such a simple shape as a unit circle. And also it's not even a function, it doesn't have an inverse function, and when you do integrals you need to use trig sub. There are so many hard things you need to do in order to deal with rotations. Then it inspires us to use, basically, to describe the same motion, but use a different kind of coordinate system, which is called the polar coordinate system. So let's think again, what do you mean by rotation? Well, when you have a rotation, imagine a point is moving here and to here and to here and to here along this way. The first thing you automatically think about is, for rotation, you have something called angular speed. So if you think about rotation centered at the origin, basically to describe where the motion, where the point is right now, you simply need to tell people what is the angle right now. Okay, because it's related to the angular speed. Whenever you have a rotation, you have a change of angles. Okay. From here you can see, since it's on a plane, knowing the angle of the location is not enough, because the point can be here, can be here, and here, can be here. Knowing the angle only gives you all the possible points on this straight ray. Then what you really should do is give people another thing. So in addition to theta, you also need to tell people how far it is on this theta line. Okay, this ray, how far is it from the origin, which we say is r. So basically, if I tell you r and theta, where r represent the distance from the origin, and then I tell you theta, which is how big the angle is, you will know the location of this particular point. And from here you can see it's very easy to use this kind of coordinate system to handle angular speed and angular rotations, simply because you have a angle related. And also you have a radius, which is r, which is also natural for rotations, because rotation usually evolves, at least locally, with respect to a circle. Okay, so that's the idea of polar coordinates. That's the definition. Okay, for xy, you have horizontal and vertical. For polar coordinates, you have r and theta. Let's do several examples. Number 1, draw the point. In polar coordinates, draw the following points. Number 1, 3, 2. We always put r first. Let me actually write it down. We always put r first and theta second. So we have 3, 2. How to draw it? Well, let's draw the polar coordinate system from here. The angle is 2. So 2 is not an easy number. We are more familiar with 0, pi over 2, and pi here, right? So pi is 3.14 something. Pi over 2 is 1.57 here. As far as we are concerned, 2 is roughly here. It's bigger than 1.57, so this is 2. That's the theta. Now, knowing the 2, you still don't know where the point is. So in order to complete, you need to go in the ray of 2 and measure a length of 3. So that's how we do it. We pick a unit. Okay, I'm just doing things randomly. And you have 3 units clearly. And then this gives you the angle 2 paired with the ratio, the radius 3. So that is where 3, 2 is. Another example. Let's try R theta equals 1, 0. So your theta is 0. That corresponds to this x-axis. You just need to go 1. Okay? And that is what you need to draw the point 1, 0. So it's not too hard. From here you can see. Let's consider a little bit about how to transform, if you have something in xy coordinates, how to transform into R theta coordinates. And if you have something in R theta coordinates, how to transform back into xy coordinates. Because later, for example, if you have something y equals 2x, that's a straight line, and you really want to know, okay, how to transform that into the same line but in polar coordinates, maybe a different former. Okay, so we need to learn how to transform between them. And the idea is really easy. Let's talk about it. Suppose you have a point. Let's talk about one direction. If you already know y, r and theta, how do you transfer it back to x and y? Through drawing. You know this is r, this is theta, this is where the point is. In order to tell people the xy coordinates, you just need to tell people how long this is and how long this is. Okay. Assuming you already know r and theta. From here you can see you can easily use a trigonometry to tell people your x is going to be r cosine theta and your y is going to be r sine theta. Okay. So to transfer from r theta to the original x and y, this will be the formula you are looking for. It's all thanks to this triangle here. If you're worried a little bit about which quadrant this one falls in, for example, if you put things in here, technically this is theta. The nice thing is r cosine theta also make your x to be negative. So there's no adjustment needed here because your theta can be anything from 0 to 2 pi or even bigger than 2 pi. Great. Now if you know the xy, okay, how do you transfer that thing to r theta? Which means if you already know this is x and y, can you find r and theta? But this time you know these two. By geometry, of course, you can see r squared equals, by Pythagorean theorem, x squared plus y squared, and then you take the square root. This will be your r. Your theta in this case is going to be, think about trigonometry, y over x is going to be tangent theta. Therefore, theta is arctangent y over x. Now, one thing you need to be careful here, that is, arctangent theta does have a range which comes from negative pi over 2 to pi over 2. That means it will be able to handle all the angles between here and here, but it will fail if you try to put an angle which is here. So for example, if this is x, this is y. Now if you do arctangent y over x, clearly this one is going to give you the angle here because it's a negative number. So I would say for things like this, always go with the positive value of y over x, but then draw the angle and justify the angles according to which quadrant it's in. Okay, but roughly this will be the formula, except for theta, you need to do additional work to figure out which quadrant it's in. Okay, let's try to think about how to do this in terms of examples. For simplicity, I will only use special angles. Okay. Let's see number 1. Let's say, here we go. We have a point xy equals -1, 1. Okay. How can you transfer it into polar coordinates? Let's draw it. -1. 1 basically means the length of these two vertical and horizontal lines are both 1, and the point here is here. Okay, Now using the formula, our r is going to be by Pythagorean theorem. That is this, right? R is going to be square root of 1 square plus 1 square, which gives you square root of 2. Okay? Your theta is going to be arctangent. Now notice, this is 1, and this is 1, so it's going to be arctangent 1 over 1, which gives you 45 degrees. But that only gives you the angle here. So to see the real theta, you actually need to use pi minus theta, which is, actually let me call this alpha. Which is actually 3 pi over 4. That's what I mean, you need to adjust for it. You cannot simply take arctangent 1 over negative 1, which gives you negative pi over 4. And that will actually give you the corresponding here because of the restriction of arctangent. Okay? But I think it's pretty easy to do. If you just ignore all the other things, only focus on the triangles, but adjust later for quadrants. Okay? Fairly easy. Now, let's think about the other way around. I have r theta. Let's just take the previous one. We have 3 pi over 6. That means we need to, number 1, give a 30 degree pi over 6. And then we go 3 units on that thing. We find the point is actually here. Okay, that's the point we're talking about. Now you want to know the x, you want to know the y. It's very easy to do. X equals r cosine theta, which is 3 times cosine pi over 6. And that gives you 3 times square root of 3 over 2, which is 2 times square root of 3. That would be your x. Your y is going to be r sine theta, which is 3 sine pi over 6, which gives you 3 times 1/2, which is 3/2. So together, your xy coordinate for this one is going to be 3 over 2 square root of 3 for x, and 3 over 2 for y. From here you can see when you have some angle involved, this one gives you the easier numbers compared to this one, which give you the trigonometry values, which are in general harder decimals. Okay, that's it. That's the idea of polar coordinates. Another way to think about it, if you still feel kind of shaky, think about coordinates in another way. That is, when we draw xy coordinates to tell people where your point is, what we really are doing is we're drawing grids. Okay, here's 1, 2, 3, 4, and here's 1, 2, 3, or whatever. So if you have a point here, we clearly know it's 2, 3 because we can count the grids. Okay, here's 2, 3, here's probably 2.1 and 3, or maybe 2.4, 3. So you can count all those grids. And so basically, you have all those kind of grids written down and try to see where the point falls. To get a better accuracy, you simply just draw more grid. You take 0.5 or maybe 0.1 as one step. You have very dense grids. But you will be able to actually write down any kind of points on the plane. Now for polar coordinates, you still draw grids. But this time your grids is going to be by different angles. So do you see the difference? They all form different angles, but they're not horizontal or vertical. It's actually star-shaped. And then for r equals 1, you have a circle because everybody on here share the same r equals 1. So you have a different kind of grid. Where do you fall really depends on where are you here or are you here, corresponding to a different angle and a different r, and anywhere in between. Okay, so it's really it's really just a different way to draw the grids whenever you do polar coordinates. Okay, so that's the idea of polar coordinates. Now, of course, we're going to go with a harder one. That is, how do you define the curves on their polar coordinates? So I will name several ones. You try to draw it, and they try to describe what shape it is. Okay, so let's say curve. Curves using polar coordinates. And later, once we have the curve, we can define derivatives and integrals. Theta equals 1. What's the shape? Well, this means r can be anything, right? So number 1, let's just find where theta equal to 1 is. This is 1.57. This is 0, so 1 is somewhere here, more than half. Okay? But now what you're trying to say is theta equals 1. And r can be anything. So basically, this one is a curve, which is actually the whole ray here. Starting from 0, 0, go all the way to infinity. Okay? If you feel confused, just think about what do you mean by y equals 1. That means x can be anything, right? So it's a horizontal line going forever. This one can also go forever. Your r can be anything. Okay. Second, r equal to 2. This one is the reverse. Your theta can be anything. It can be here, it can be here, it can be here, it can be here, it can be here. As long as you make sure the distance here are all 2, from here it's not easy, it's not hard to see. This is actually a circle with radius 2. And from here you can already see the advantage of polar coordinates. That is to define a circle. This is way better than what we need to write down here for xy coordinates. So for rotations, polar coordinate is really natural. Okay, let's try something a little bit harder. Let's try r equal theta. Well, if this is xy coordinates, we know this is a straight line. That's y equals x, right? What is r equals theta? What does it mean? Take a while, think about it, and let's try. This one means theta become bigger, then r also become bigger. That means for this angle here, if I go this far, for a bigger angle, I go a little bit further. For even bigger angle, I go even a little bit further. From here, it's not hard to see. We should have a circle type of thing, but the radius keep becoming bigger as you start to rotate your angle from here all the way up. Okay. So it's going to be something like that to make sure everything is just getting bigger. So it's a spiral. Okay. Think again, your theta rotates. And as your theta rotates, your distance from your point to the origin becomes bigger and bigger and bigger. That's why all these points get further, further, and further away as you increase the theta. And this one can actually go forever. Okay, so that's a spiral which never ends. Moreover, if you really want a detailed number, because r equals theta, and this one happens when theta equals pi over 2, that means the distance from 0 to here is also pi over 2. Okay, this is probably 2 pi, which means the distance from here to here is 2 pi, and so on. Okay, that's after a complete cycle where theta equals 2 pi. Good. Do we have something else? Well, let's try r equal cosine theta. This one's kind of tricky because we know it's periodic. Number 2, sometimes cosine theta is positive, sometimes cosine theta is negative. For negative r, it's kind of tricky. Okay, so let's think about it. Here are the case. You do know cosine theta. You do know several special points of cosine theta. So let's write it down. At 0, it's 1. Okay, at pi over 2, it's 0. Okay, at pi, it's negative 1. And at 3 pi over 2, it's 0. And then at 2 pi, it becomes 1 again, not complete one cycle. Let's try to draw it period by period. Let's talk about how do we go from here to here. That means when your theta is 0, your r is 1, which is cosine theta, right? So when theta is 0, you're here. And then as your theta rotate from here to here, what's going to happen is the r becomes smaller and smaller. So if you think about it, this is actually the furthest. As far as your thing is moving here, you actually move closer to the origin. And when you hit pi over 2, you actually hit 0. So what you have is actually something that, like this. As your angle becomes bigger, your r becomes shorter. Okay. Moreover, when you hit angle pi over 2, you have 0. So that's the first piece. Now the second piece, your angle is here, okay, for example, but your r should be negative because cosine theta, let me put it here. For this period, your cosine theta are both negative. It went from 0 all the way to -1. So at first you start from 0, and eventually when you are here, which is pi, your r is -1. That means you take this angle pi, but go opposite for 1. You reach here. So if you try to draw it, it's actually nothing but this. Oh, what's going on here? Okay. Hopefully you followed. Okay. That's what happened for this part. Now for the third part, you actually do the same thing again. You are still here, right? You actually go, your angle go this way. But again, your r is negative. That means your real point should be on the other side. Even though your angle is here, your real point is negative, your r, so you should go the other side. So you repeat this process. That is the third time. And then I will skip the fourth time, but I think you get what I mean here. Okay, so for this graph, it's actually a circle centered at 1/2, 0, with a radius 1/2, and it goes around the whole circle for twice. Okay, within a one single period between pi and 0 and between 0 and pi 0 and 2 pi. So that's what we have here. Okay. Does it make sense? If it does, now if you think about it, we actually have some way of doing this to see it's a circle. This is the formula, right? Let's try to change it to be xy formula. Now, this is almost y. X, if you just times another r, that will give you r squared here. Times r on both sides, still okay? Actually, let me put it here. To see it's a circle, we start from this one, and we times r on both sides. Now you can see it's x squared plus y squared for r squared, and you can change this whole thing here to be x. So this will be the xy formula. For this polar coordinates formula, r equals cosine theta. Now if you do a little bit of manipulation here, complete the square, you will get this, which is exactly the circle, centered at 1/2, 0, with r equals 1/2. Okay, that's how you got the circle here. Okay, you don't have to do this every time when you see a polar coordinate curve. You can just draw it as I did, but I just did this to show you the solid computation that this is actually a circle. Okay? That's probably a harder one, but now let's take an even harder one. This time I put a 2 here. You've done enough. I would suggest you to actually pause here and try to draw it yourself, because I'm not going to pause when I make the video. I just go ahead and draw it. But you should pause a little bit and think about how this graph is going to form. Okay, I'm ready to give you the answer. So pause by yourself. You have cosine 2 theta. Okay, and here's your theta. If your theta is 0, this is 1. So you start from 1, 0. Okay. The next time you see this one is actually when theta equals pi over 4. You have cosine pi over 2, you already reach 0. That means you go all the way But when the theta is here, you already hit 0. So you have something like this. Okay, for the first part. Now going from pi over 4 to pi over 2. Your cosine 2 theta went from 0 to -1. So that means starting from here, your r is actually here on the opposite side because your r is going to be negative, right? So for this angle, you're here. And then eventually you are at -1. Try to follow what I do. I really shouldn't have done this. Okay. Yeah, probably that's a good idea. What you get for the second part should be go all the way. Oh. Go all the way up to here, which is -1. Okay, take a look at what I did here. Basically, your real angle is here. But because your r is negative, that's why your point is pointing this way. So that's how you actually draw the whole thing in quadrant 3. Sounds good. Now what I'm going to do is I'm going to go from pi over 2 to 3 pi over 4. Okay, I'm going really quick here. Pause anytime. Then your cosine 2 theta went from -1 to 0 again. Let me use green for this time. So your angle is actually between here and here. Okay, for this one, you're still negative. You're here, right? For this one, you are here. Okay, you always go with the opposite. So what you do is you complete another leaf. And I think so far, up to now, you probably have a strong belief all the shapes should look identical or symmetric. It's just at different location. That's the third part. Okay. Fourth part, you go to 0 to 1 again. And then I will skip all the detail. You do it by yourself, but I will complete the graph. That's what's going to happen, okay? Within one complete cycle from 0 to 2 pi. I did the first 3. Starting from there, try to complete by yourself, but that's the graph of this cosine 2 theta. Sounds good? Okay. Now, this may take some time, so if you are slow on this, that's totally natural. Try to draw it, and even better, try to make up several examples for yourself to try to draw multiple of them, and finally you get an idea of what's going on. I will give you one more example, and then I will show you how to graph all those kind of things using software from Desmos. But let's just take this one. Now you're probably already familiar with this. This one is going to be periodic. You just repeat. Okay. What you really care about is decompose them into several parts. From 0, you have 1. From pi over 2, you have 0. Oh, sorry. It's different now. It's r plus cosine theta. So when you have 0, you have 2. When you have pi over 2, you have 1, which is the shortest. Not the shortest, which is now 0. When you have pi, you have -1 for cosine theta, so your r equals 0. And when you have 3 pi over 2, you have 1 again. And when you have 2 pi, what am I? Yes. When you have 2 pi, you have cosine 0, you have 2 again. Okay. So first is when theta is 0, you actually have 2. So this is 2. Sounds good? When theta is pi over 2, which means when you are at this point, you are at 1. So if this is 2, this is 1. And when you go from here to here, your radius becomes smaller and smaller and smaller and smaller. So this is basically what you got. I'm really bad at drawing, but I will try my best. That's what we got. Okay. Now going from pi over 2 into this quadrant, your r is still positive, but keeps becoming smaller until you finally hit the origin, which becomes 0. So you're going to have something like that. Okay. Cool. And then when you have radius, when you have enter this realm, you actually start to go from 0 to 1 again. So as you go further, your r actually becomes bigger until eventually you hit 1 again for 3 pi over 2. And finally, you repeat the whole process all the way back to what you have here. That's what the shape of this is. I call it a butt function. Some people call it a peach, whatever. But really, it's just a butt function. And we will be using this one a lot to illustrate further examples. Okay, that's all we got for how to draw those kind of things. Of course, it's kind of tricky at first, but take your time. Try to do more by yourself. There's no shortcut for this. But the good news is once you have done, I will give you a number. If you have done the drawing of polar coordinates with considerable difficulty, something like this, after you draw 10 of them, you will start to see what's going on. Okay. Now let me show you how to do it in Desmos. In Desmos, you basically just type in the function in this way. Okay, r equals cosine theta. From here you can see it's a straight line. It's a circle centered at 1/2 with radius 1/2. Okay, just make sure you use these two letters. Okay, if you use cosine A, cosine B, cosine alpha, cosine beta, it won't work. It only recognizes theta. Okay, so you have to use special letters. Now, to talk about the one we just did, we do r equals. Actually, why don't we just change it from here? R equals cosine 2 theta. Okay, that's exactly what we draw. Great. Now I'm going to ask you a question. What will happen if I change this to be cosine 3 theta? Make a guess. Pause. Make a guess. And here's the answer. Okay, 4 theta. 5 theta. 6 theta. Okay, that's pretty interesting format. Now I want to challenge you this. How many leaves are there if you do 2 theta? 4, right? How many leaves are there when you have 3 theta? You should have 6. But instead you have 3. Okay, but what about 4 theta? I should have 4 leaves, right? But if you do it, this is really a pain in the butt. So you need to do theta. Okay. You are back to 8 leaves again. And then 5, you're supposed to have 10, but then you only have 5. Then for 6, why don't you have 6? Instead you have 12. It seems like for all the double angles, okay, angle with double frequency, what you have is you have twice the size of the integer I put there. For example, if I put a 4, I have 8 leaves. If I put 6, I have 12 leaves. But for all the odd ones, I don't have double. For 5, I have 5. For 3, I have 3. And you can guess for 7, I have 7. Okay, but for 8, I definitely have 18. Question is, why is that? Think about it by yourself. Okay. Now, finally, let's go back to the butt function. That is going to be r equals 1 plus, okay, cosine theta. That's the butt function, nice and clear. Okay, that is great. Now what I want you to do is think about what if I change this to be sine. Okay, it seems like what's going on is you took r equals cosine 1 plus cosine theta, you change cosine to be sine, you basically rotate it by 90 degrees. Does that make sense here? Well, if you think about it, it kind of makes sense. So r equals 1 plus cosine theta. Now here is r equals 1 plus sine theta. Now we do know there is a way to write sine theta to be cosine theta, which is cosine. Let's just take a easy case. Cosine theta plus pi over 2. Minus. Take it back. Okay, this is the identity which you can easily verify. But basically what you are saying is, this one has a graph look like this way. Okay, now this one is basically the same thing, except you change theta to be theta minus pi over 2. Now if you think about it, that means in all the new theta, you should be pi over 2 bigger than the old theta to get the same r. That means exactly rotating the whole thing by 90 degrees. This way. Why? For example, if you want 0 to get the corresponding r, this time you need pi over 2 to get the corresponding r. If you want, I would say, pi over 4 to get the corresponding r here, this time you really do need this one plus pi over 2, 3 pi over 4 to get the corresponding r here, because it's now becoming here. Sounds good? Okay, so that's actually rotation, a shift. Think about what's going to happen if you do fx, okay, and change it to be fx minus 2. You shift the whole thing to the right by 2. Right? That's how we do function transformations. Now if you do r theta, you change it to be r theta minus pi over 2. You similarly you shift it to the right by pi over 2. But what do you mean by shifted the angle to the right? That means you rotate the angle, okay, in the positive direction by pi over 2. So that's another advantage you can see from here. If you change theta, you actually rotate the whole thing. Okay? Great. That's what we have for that example. You can try, change cosine to be sine, you just rotate it. And you can rotate it for any angle, actually. You don't have to be just exactly pi over 2. Now, finally, the interesting thing. We have theta. Okay, which looks like that. I agree. Now the question is, what if I put 2 here? Try to imagine. What if I put a 3 here? Do you realize we just get exactly what we got from the top? Except everything got rotated. Okay? It's not actually exactly falling on horizontal and vertical anymore, but still you got the same kind of shape. Okay? Why is that? Go back, think about it, and I will challenge everybody who is watching this video to come up with interesting ways to generate interesting graphs using polar coordinates, because think about it, no matter what kind of graph you put in there, as long as it's easy, you're always going to generate something with a symmetry, because this is related to rotations. Okay, so go there and play with it and try to create some nice graphs by yourself. But I think that's all. I just noticed one thing I forgot to point out is R theta. For example, you have 2, 3. Oh, let's just to take an easy one. Okay, let's take 2 pi over 2, which we definitely know how to draw. It's going to be pi over 2, and you just go a distance of 2. That's 2 pi over 2. But when you do it, if you put a negative sign here, what's going to happen? Because according to our understanding, our r should always be positive, right? It's actually going to work. Basically, what you do is you still take the same angle, which is pointing up, and your r are supposed to be going this way, but if it's negative, you simply go the other way. So this is actually 2 pi over 2 with the negative 2. That means technically my angle is here, but I go negative in the negative direction for my r. That's how I end up here. Okay, so if you have a negative in r, this is how you treat it. But then you have another question that is really interesting, because for this point, there are so many ways to present it. It can be 1, 0. It can also be, if you think about the angle is pi, then it's negative 1 pi. Okay, so this point can simultaneously be both this, and it very well should be so, because once you do unit circle, right, you kind of know whenever you see an angle, for example, you see an angle like that, this certainly is pi over 6, but you can also make it to be 5 pi over 6. No, sorry. It's 13 pi over 6. You have all this kind of periodic information. So yes, we can have multiple representations of the same point, but they really shouldn't bother too much. Okay, as long as you can find the right one representation doing what you need, you're probably fine. Okay, so that's what we have now. Next, let's talk about distance formula. If you have 2 points, what is the difference between them? And for rectangular, it's super easy. It's just the Pythagorean theorem. Okay, if you have x1, x2, y2, x1, y1, you simply take x1 minus x2 and take y1 minus y2 to give you the horizontal and vertical, and then you use the Pythagorean theorem. Okay, and it really doesn't matter which one goes first. You can use x2 minus x1 or x1 minus x2 because you're going to square them either way. That's why the distance between these two, this first, this second, or the distance, if you switch the order between these two, are the same. It's like the distance between you and me is the same as the distance between me and you. Okay, it's the same. Now, of course, we have a different one. Actually, let me just show you my notes. We have 2 point, r1 theta 1, which is here, r2 theta 2, which is here, and we want to find the distance between them. From here, you can see we just simply apply the law of cosine. Okay, the law of cosine, which is r1 squared plus r2 squared minus 2r1 r2 cosine theta 1 minus theta 2, because technically we're taking this angle in between. Okay, theta 2 goes this from here all the way to the x-axis. Theta 1 also goes here, so we're taking the difference. It doesn't matter if you do theta 1 minus theta 2 or theta 2 minus theta 1, because cosine x is a even function, so it's really not that difficult. Okay, the next thing we want to talk about are the symmetries, which is also a natural extension of what we have for rectangulars. Every time you have something in rectangular, you probably want to do the same thing in polar coordinates or parametric. I don't know what's going on with my notes, but let's see. So think about what kind of symmetry we had before for x. You know we have something called even function, y equals x squared, right? So what we have basically is we take a reflection with respect to the y-axis, and then we have the reflection with respect to x-axis, and then we have the reflection with respect to the origin. So we have these three type of symmetries. Let's list them here. We have with respect to the x-axis, y-axis, and the origin. So if you have x and y to reflect over the x-axis, you simply think about it, x negative y. Okay. If you have y-axis, you simply take negative xy. And for origin, you take negative x and negative y. So if you want to take a graph, here's xy. With respect to x-axis will be this point. That's x negative y. With respect to y-axis will be this point. That will be negative xy. And then, of course, this one is negative x and negative y. That's the definition of odd function, right? Symmetric with respect to the origin. Okay, now for r theta in terms of polar coordinates. How do you get them? Well, it's actually pretty straightforward. If this is r theta, with respect to x-axis, how do you represent this point here, which is symmetric? Well, as far as we can see, they share the same r. The r here will be the same as the r here, right? So r is the same. Your theta is different. This is theta. The angle for this one is going to be this. And that is just negative theta. So it works. What about this one? Okay, that's symmetric with respect to the origin. Well, if you take this one to be theta, this is basically going in the opposite direction of theta. What you can do is you can actually take the same r but make it negative. Or, to take an alternative, you can take the same r, but you do theta plus pi to make sure this angle got migrated to this one. Either way, actually, it will work. So there's really no preference. Similarly, what about this one? You can see you keep the same r, but this is going to be theta. If you want a symmetry with respect to the y-axis, That gives you the real theta to be pi minus theta. So I put all these kind of things as a list here. Go back and play with it and try to see how we got all these conclusions. It's very easy. Cool. So finally, what we want to talk about is how to use polar. Okay, I guess my iPad is starting to malfunction once in a while, but either way, we have the last thing to talk about. That is, how do we take the derivatives? How do we find the tangent lines? Okay, so to give you some ideas, at least we should be able to find, circle are boring, but let's take the but function. R equals 1 plus cosine theta, right? At least we should be able to find the tangent line here, maybe the tangent line here, or name any points you want. Or we can find actually for which angle this one reach the exact horizontal place. Okay? And since all these kind of shapes are weird if you present them into xy coordinate, of course you have to do it through polar coordinates. Okay? So we will do the detail of the example later, but let's talk about how to do it. Remember, the slope of the tangent line is always dy over dx. Now before, if we have x equals to a function of t and the y equals to a function of t, that's generally parametric, right? What we do is we do dy over dt and dx over dt. That is the derivative of each. And then these dt and dt cancel each other. That's where you got all these. That's how you transform the variable to, instead of taking the derivative with respect to x, you take it with respect to t. But they eventually cancel. Okay? Now here's the problem. The problem we have here is we don't have t anymore. We do have r and theta. Then probably a nice way to do it is actually, not only we have r theta, our r is also a function of theta. That's how we define a curve. Remember, like r equals 1 plus cosine theta. So we know exactly what this f theta is. So probably we don't want to do t. Instead, we want to do theta. That should also work. All right. That is good. So dy over d theta and dx over d theta. But now what is your y? In terms of r theta, that's r sine theta. And the derivative of r cosine theta, which is your dx, if we plug in even more, because we want to transfer everything in terms of r and theta. Good so far? Okay, so that's your y, that's your x. Now when you start to take the derivatives, you need to think about who are they. Is r constant? No, r depends on theta. Is sine theta constant? No, it also depends on theta. So what you see here is the product of two functions of theta. That means naturally we should do the product rule, which is dr over d theta. Okay, sine theta. Do the first one, keep the second one, plus keep the first one, and the second one. And the second one, you have r times the derivative of sine theta with respect to theta is cosine theta. Similarly, dr over d theta, cosine theta, r, the derivative of cosine theta, which is negative sine theta. So that is going to be the formula of how to take the derivative of dy over dx, which is the slope of the tangent line, using purely r and theta. What you do is you use the parametric and change everything to be d theta instead of dt. But once you have that, change your y and x to be r theta, which is how we transform from r theta to xy, and then do the product rule there. That's how we do this. Okay, that's the formula here. Let me show you some examples. And later we will show you actually you don't have to memorize anything. Okay, this looks like a messy formula to be memorized. So that's number 3. Let's do number 4. That is, let's try to find the slope of the tangent line at, of this but function r equals 1 plus cosine theta at theta equals pi over 3. Okay, that's what we're trying to do. Now, let's take a look by drawing. We know the path function look kind of like this. This is roughly where pi over 3 is, and you are going to have a tangent line. We want to find the slope here. That is going to be dy over dx. Okay. When we finish, we should have everything with in terms of theta. Then we plug in theta equals pi over 3. Now, if you want to memorize the formula, it's totally fine. But I suggest you don't do it. Okay? Number 1, this is dy over d theta. Dx over d theta. Alright? Now, what is your y? Your y is r cosine theta. And your x is going to be r sine theta. Good so far? Now, instead of memorizing the formula, what is your r? Your r is 1 plus cosine theta. That's how you draw the graph. Then why don't you just put 1 plus cosine theta here? You're basically just taking the derivative of this with respect to theta and the derivative of this with respect to theta. Okay? Since everything's in order, but keep in mind this is already your r. So if you want to follow the formula, that's fine. But if you don't follow the formula, basically what you're trying to say is, let's take the derivative of this, which is cosine theta plus cosine square theta. And the derivative of this, sine theta plus sine theta cosine theta. That's how we're going to do the derivatives. Then what you really got here is going to be negative sine theta plus 2 cosine theta times